Carrier transport phenomena. In the previous chapter, we considered the semiconductor in equilibrium and determined electron and hole concentrations in the conduction and valence bands, respectively. A knowledge of the densities of these charged particles is important toward an understanding of the electrical properties of a semiconductor material. The net flow of the electrons and holes in a semiconductor will generate currents. The process by which these charged particles move is called transport. In this chapter we consider two basic transport mechanisms in a semiconductor crystal: drift, the movement of charge due to electric fields, and diffusion, the flow of charge due to density gradients. The carrier transport phenomena are the foundation for finally determining the current voltage characteristics of semiconductor devices. We will implicitly assume in this chapter that, although there will be a net flow of electrons and holes due to the transport processes, thermal equilibrium will not be substantially disturbed. Non-equilibrium processes are considered in the next chapter. Preview. In this chapter, we will describe the mechanism of carrier drift and induced drift current due to an applied electric field. Define and describe the characteristics of carrier mobility. Describe the mechanism of carrier diffusion and induced diffusion current due to a gradient in the carrier concentration. Define the carrier diffusion coefficient. Describe the effects of a non-uniform impurity doping concentration in a semiconductor material. Discuss and analyze the Hall effect in a semiconductor material. Carrier drift. An electric field applied to a semiconductor will produce a force on electrons and holes so that they will experience a net acceleration and net movement, provided there are available energy states in the conduction and valence bands. This net movement of charge due to an electric field is called drift. The net drift of charge gives rise to a drift current. Drift current density. If we have a positive volume charge density moving at an average drift velocity Vd, the drift current density is given by. In terms of units, we have. If the volume charge density is due to positively charged holes, then where Js the drift current density due to holes and Vdp is the average drift velocity of the holes. The equation of motion of a positively charged hole in the presence of an electric field is where E is the magnitude of the electronic charge, A is the acceleration, E is the electric field, and mCp asterisk is the conductivity effective mass of the hole. 1. If the electric field is constant, then we expect the velocity to increase linearly with time. However, charged particles in a semiconductor are involved in collisions with ionized impurity atoms and with thermally vibrating lattice atoms. These collisions, or scattering events, alter the velocity characteristics of the particle. As the hole accelerates in a crystal due to the electric field, the velocity increases. When the charged particle collides with an atom in the crystal, for example, the particle loses most, or all, of its energy. The particle will again begin to accelerate and gain energy until it is again involved in a scattering process. This continues over and over again. Throughout this process, the particle will gain an average drift velocity which, for low electric fields, is directly proportional to the electric field. We may then write where U is the proportionality factor and is called the hole mobility. The mobility is an important parameter of the semiconductor since it describes how well a particle will move due to an electric field. Table 5.1 Typical mobility values at T300 K and low doping concentrations. The unit of mobility is usually expressed in terms of square centimeters per volt seconds. By combining equations 5.2 and 5.4, we may write the drift current density due to holes as the drift current due to holes is in the same direction as the applied electric field. The same discussion of drift applies to electrons. We may write where J is the drift current density due to electrons and Vdn is the average drift velocity of electrons. The net charge density of electrons is negative. The average drift velocity of an electron is also proportional to the electric field for small fields. However, since the electron is negatively charged, the net motion of the electron is opposite to the electric field direction. We can then write where n is the electron mobility and is a positive quantity. Equation 5.6 may now be written as: the conventional drift current due to electrons is also in the same direction as the applied electric field, even though the electron movement is in the opposite direction. Electron and hole mobilities are functions of temperature and doping concentrations, as we will see in the next section. Table 5.1 shows some typical mobility values at T300 K for low doping concentrations. Since both electrons and holes contribute to the drift current, the total drift current density is the sum of the individual electron and hole drift current densities, so we may write: objective, calculate the drift current density in a semiconductor for a given electric field. Consider a gallium arsenide sample at temperature equals 300 kelvins with doping concentrations of N acceptors equals 0 and N donors equals 10^16 per cubic centimeter. Assume complete ionization and assume electron and hole mobilities given in table 5.1. Calculate the drift current density if the applied electric field is E equals 10 volts per centimeter. Solution: since N donors is greater than N acceptors, the semiconductor is N-type and the majority carrier electron concentration, from chapter 4, is given by the minority carrier hole concentration is. For this extrinsic N-type semiconductor, the drift current density is. Then. Comment. Significant drift current densities can be obtained in a semiconductor applying relatively small electric fields. We may note from this example that the drift current will usually be due primarily to the majority carrier in an extrinsic semiconductor. Mobility effects. In the previous section, we defined mobility, which relates the average drift velocity of a carrier to the electric field. Electron and hole mobilities are important semiconductor parameters in the characterization of carrier drift, as seen in equation 5.9. Equation 5.3 related the acceleration of a hole to a force such as an electric field. We may write this equation as: where v is the velocity of the particle due to the electric field and does not include the random thermal velocity. If we assume that the conductivity, effective mass and electric field are constants, then we may integrate equation 5.10 and obtain where we have assumed the initial drift velocity to be 0. Figure 5.1 shows a schematic model of the random thermal velocity and motion of a hole in a semiconductor with 0 electric field. There is a mean time between collisions which may be denoted by TCP. Figure 5.1 typical random behavior of a hole in a semiconductor: A, without an electric field, and B, with an electric field. Figure 5.1 typical random behavior of a hole in a semiconductor: A, without an electric field, and B, with an electric field. If a small electric field, E field, is applied as indicated in figure 5.1b, there will be a net drift of the hole in the direction of the E field, and the net drift velocity will be a small perturbation on the random thermal velocity, so the time between collisions will not be altered appreciably. If we use the mean time between collisions Cp in place of the time t in equation 5.11, then the mean peak velocity just prior to a collision or scattering event is. The average drift velocity is 1/2 the peak value, so that we can write. However, the collision process is not as simple as this model, but is statistical in nature. In a more accurate model including the effect of a statistical distribution, the factor 1/2 in equation 5.12b does not appear. The hole mobility is then given by. The same analysis applies to electrons, thus, we can write the electron mobility as where Cn is the mean time between collisions for an electron. There are two collision or scattering mechanisms that dominate in a semiconductor and affect the carrier mobility: phonon or lattice scattering, and ionized impurity scattering. The atoms in a semiconductor crystal have a certain amount of thermal energy at temperatures above absolute zero that causes the atoms to randomly vibrate about their lattice position within the crystal. The lattice vibrations cause a disruption in the perfect periodic potential function. A perfect periodic potential in a solid allows electrons to move unimpeded, or with no scattering, through the crystal. but the thermal vibrations cause a disruption of the potential function, resulting in an interaction between the electrons or holes and the vibrating lattice atoms. This lattice scattering is also referred to as phonon scattering. Since lattice scattering is related to the thermal motion of atoms, the rate at which the scattering occurs is a function of temperature. If we denote U as the mobility that would be observed if only lattice scattering existed, then the scattering theory states that to first order mobility that is due to lattice scattering increases as the temperature decreases. Intuitively, we expect the lattice vibrations to decrease as the temperature decreases, which implies that the probability of a scattering event also decreases, thus increasing mobility. Figure 5.2 shows the temperature dependence of electron and hole mobilities in silicon. In lightly doped semiconductors, lattice scattering dominates and the carrier mobility decreases with temperature, as we have discussed. The temperature dependence of mobility is proportional to temperature. The inserts in the figure show that the parameter n is not equal to 3/2 as the first-order scattering theory predicted. However, mobility does increase as the temperature decreases. The second interaction mechanism affecting carrier mobility is called ionized impurity scattering. We have seen that impurity atoms are added to the semiconductor to control or alter its characteristics. These impurities are ionized at room temperature so that a Coulomb interaction exists between the electrons or holes and the ionized impurities. This Coulomb interaction produces scattering or collisions and also alters the velocity characteristics of the charge carrier. If we denote I as the mobility that would be observed if only ionized impurity scattering existed, then to first order we have where n equals n donors plus n acceptors is the total ionized impurity concentration in the semiconductor. If temperature increases, the random thermal velocity of a carrier increases, reducing the time the carrier spends in the vicinity of the ionized impurity center. The less time spent in the vicinity of a Coulomb force, the smaller the scattering effect and the larger the expected value of I. If the number of ionized impurity centers increases, then the probability of a carrier encountering an ionized impurity center increases, implying a smaller value of U. Figure 5.3 is a plot of electron and hole mobilities in germanium, silicon, and gallium arsenide at temperature equals 300 kelvins as a function of impurity concentration. More accurately, these curves are of mobility versus ionized impurity concentration Ni. As the impurity concentration increases, the number of impurity scattering centers increases, thus reducing mobility. If L is the mean time between collisions due to lattice scattering, then dTus the probability of a lattice scattering event occurring in a differential time dt. Likewise, if I is the mean time between collisions due to ionized impurity scattering, then dTi is the probability of an ionized impurity scattering event occurring in the differential time dt. Figure 5.2, a. Electron and b. hole mobilities in silicon versus temperature for various doping concentrations. Inserts show temperature dependence for almost intrinsic silicon. Figure 5.3 Electron and hole mobilities versus impurity concentrations for germanium, silicon, and gallium arsenide at temperature equals 300 kelvins. If these two scattering processes are independent, then the total probability of a scattering event occurring in the differential time dt is the sum of the individual events, or where t is the mean time between any scattering event. Comparing equation 5.17 with the definitions of mobility given by equation 5.13 or 5.14, we can write where U is the mobility due to the ionized impurity scattering process and U is the mobility due to the lattice scattering process. The parameter U is the net mobility. With two or more independent scattering mechanisms, the inverse mobilities add, which means that the net mobility decreases. Objective: determine the electron mobility in silicon at various doping concentrations and various temperatures. Using figure 5.2, find the electron mobility in silicon for a. temperature equals 25 degrees Celsius for I, n donors 10 power 16 per cubic centimeter and 2, n donors 10 power 17 per cubic centimeter. b. N donors 10 power 16 per cubic centimeter for I, temperature equals 0 degrees Celsius and 2, temperature equals 100 degrees Celsius. Solution. From figure 5.2, we find the following. A. Temperature equals 25 degrees Celsius, I, N donors equals 10 power 16 per cubic centimeter U equals 1200 square centimeters per volt seconds. 2. N donors equals 10 power 17 per cubic centimeter U equals 800 square centimeters per volt seconds. B. N donors equals 10 power 16 per cubic centimeter, I, T temperature equals 0 degrees Celsius U equals 1400 square centimeters per volt seconds. 2. Temperature equals 100 degrees Celsius U equals 780 square centimeters per volt seconds. Comment. The results of this example show that the mobility values are strong functions of the doping concentration and temperature. These variations must be taken into account in the design of semiconductor devices. Conductivity. The drift current density, given by equation 5.9, may be written as where sigma is the conductivity of the semiconductor material. The conductivity is given in units of centimeters per ohm and is a function of the electron and hole concentrations and mobilities. We have just seen that the mobilities are functions of impurity concentrations. Conductivity, then, is a somewhat complicated function of impurity concentration. The reciprocal of conductivity is resistivity, which is denoted by N is given in units of ohms per centimeter. We can write the formula for resistivity as Figure 5.4 is a plot of resistivity as a function of impurity concentration in silicon, germanium, gallium arsenide, and gallium phosphide at temperature equals 300 kelvins. Obviously, the curves are not linear functions of N donors or N acceptors because of mobility effects. Figure 5.4 resistivity versus impurity concentration at temperature equals 300 kelvins in A. Silicon and B. Germanium, gallium arsenide, and gallium phosphide. Figure 5.5 bar of semiconductor material as a resistor. If we have a bar of semiconductor material as shown in figure 5.5 with a voltage applied that produces a current I, then we can write. And we can now rewrite equation 5.19 as or equation 522b is Ohm's law for a semiconductor. The resistance is a function of resistivity, or conductivity, as well as the geometry of the semiconductor. If we consider, for example, a p-type semiconductor with an acceptor doping Na, North Dakota equals 0, in which Na is more than N intrinsic, and if we assume that the electron and hole mobilities are of the same order of magnitude, then the conductivity becomes. If we also assume complete ionization, then equation 5.23 becomes. The conductivity and resistivity of an extrinsic semiconductor are a function primarily of the majority carrier parameters. Figure 5.6 electron concentration and conductivity versus inverse temperature for silicon. We may plot the carrier concentration and conductivity of a semiconductor as a function of temperature for a particular doping concentration. Figure 5.6 shows the electron concentration and conductivity of silicon as a function of inverse temperature for the case when N donors equals 10 power 15 per cubic centimeter. In the mid-temperature range, or extrinsic range, as shown, we have complete ionization. The electron concentration remains essentially constant. However, the mobility is a function of temperature, so the conductivity varies with temperature in this range. At higher temperatures, the intrinsic carrier concentration increases and begins to dominate the electron concentration as well as the conductivity. In the lower temperature range, freeze-out begins to occur, the electron concentration and conductivity decrease with decreasing temperature. Objective: determine the doping concentration and majority carrier mobility given the type and conductivity of a compensated semiconductor. Consider compensated N-type silicon at temperature equals 300 kelvins, with a conductivity of 16 ohms per centimeter and an acceptor doping concentration of 10 power 17 per cubic centimeter. Determine the donor concentration and the electron mobility. Solution. For N-type silicon at temperature equals 300 kelvins, we can assume complete ionization, therefore the conductivity, assuming N donors minus N acceptors is greater than Ni, is given by. We have that. Since mobility is a function of the ionized impurity concentration, we can use figure 5.3 along with trial and error to determine U and N donors. For example, if we choose N donors 2 times 10 power 17, then N equals N donors plus N acceptors equals 3 times 10 power 17 so that U equals 510 square centimeters per volt seconds, which gives sigma equals 8.16 ohms per centimeter. If we choose N donors equals 5 times 10 power 17, then U equals 6 times 10 power 17 so that U 325 square centimeters per volt seconds, which gives sigma equals 20.8 ohms per centimeter. The doping is bounded between these two values. Further trial and error yields N donors equals 3.5 times 10 power 17 per cubic centimeter, and U equals 400 square centimeter per volt seconds, which gives sigma equals 16 ohms per centimeter. Comment. We can see from this example that, in a high conductivity semiconductor material, mobility is a strong function of carrier concentration. Objective: design a semiconductor resistor with a specified resistance to handle a given current density. A silicon semiconductor at temperature equals 300 kelvins is initially doped with donors at a concentration of N donors equals 5 times 10 power 15 per cubic centimeter. Acceptors are to be added to form a compensated P-type material. The resistor is to have a resistance of 10 kilo ohms and handle a current density of 50 amperes per square centimeter, when 5V is applied. Solution. For 5 volts applied to a 10 kilo ohm resistor, the total current is. If the current density is limited to 50 amperes per square centimeter, then the cross-sectional area is. If we, somewhat arbitrarily at this point, limit the electric field to E equals 100 volts per centimeter, then the length of the resistor is. From equation 522b, the conductivity of the semiconductor is. The conductivity of a compensated P-type semiconductor is. Where the mobility is a function of the total ionized impurity concentration N acceptors plus N donors. Using trial and error, if N acceptors equals 1.25 times 10 power 16 per cubic centimeter, then N acceptors plus N donors equals 1.75 times 10 power 16 per cubic centimeter, and the whole mobility, from figure 5.3, is approximately U equals 410 aquar centimeters per volt seconds. The conductivity is then. Which is very close to the value we need. Comment. Since the mobility is related to the total ionized impurity concentration, the determination of the impurity concentration to achieve a particular conductivity is not straightforward. For an intrinsic material, the conductivity can be written as: the concentrations of electrons and holes are equal in an intrinsic semiconductor, so the intrinsic conductivity includes both the electron and hole mobility. Since, in general, the electron and hole mobilities are not equal, the intrinsic conductivity is not the minimum value possible at a given temperature. Velocity saturation. So far in our discussion of drift velocity, we have assumed that mobility is not a function of electric field, meaning that the drift velocity will increase linearly with applied electric field. The total velocity of a particle is the sum of the random thermal velocity and drift velocity. At temperature equals 300 kelvins, the average random thermal energy is given by. This energy translates into a mean thermal velocity of approximately 10 million centimeters per second for an electron in silicon. If we assume an electron mobility of N1 equals 350 square centimeters per volt seconds. In low-doped silicon, a drift velocity of 500,000 centimeters per second, or 1% of the thermal velocity, is achieved if the applied electric field is approximately 75 volts per centimeter. This applied electric field does not appreciably alter the energy of the electron. Figure 5.7 is a plot of average drift velocity as a function of applied electric field for electrons and holes in silicon, gallium arsenide, and germanium. At low electric fields, where there is a linear variation of velocity with electric field, the slope of the drift velocity versus electric field curve is the mobility. Figure 5.7 carrier drift velocity versus electric field for high-purity silicon, germanium, and gallium arsenide. The behavior of the drift velocity of carriers at high electric fields deviates substantially from the linear relationship observed at low fields. The drift velocity of electrons in silicon, for example, saturates at approximately 10 million centimeters per second at an electric field of approximately 30 kilovolts per centimeter. If the drift velocity of a charge carrier saturates, then the drift current density also saturates and becomes independent of the applied electric field. The experimental carrier drift velocity versus electric field in silicon can be approximated for electrons by and for holes by. The variables are versus equals 10 million centimeters per second at temperature equals 300 kelvins, EON equals 7,000 volts per centimeter, and EOP equals 20,000 volts per centimeter. We may note that for small electric fields, the drift velocities reduce to and. At low electric fields, the drift velocities are linear functions of the electric field as we have discussed. However, for large electric fields, the drift velocities approach the saturation value. The drift velocity versus electric field characteristic of gallium arsenide is more complicated than for silicon or germanium. At low fields, the slope of the drift velocity versus E field is constant and is the low field electron mobility, which is approximately 8,500 square centimeters per volt seconds for gallium arsenide. The low field electron mobility in gallium arsenide is much larger than in silicon. As the field increases, the electron drift velocity in gallium arsenide reaches a peak and then decreases. A differential mobility is the slope of the Vd versus E curve at a particular point on the curve, and the negative slope of the drift velocity versus electric field represents a negative differential mobility. The negative differential mobility produces a negative differential resistance. This characteristic is used in the design of oscillators. The negative differential mobility can be understood by considering the E versus K diagram for gallium arsenide, which is shown again in figure 5.8. The density of state's effective mass of the electron in the lower valley is m*n 0.067 m0. The small effective mass leads to a large mobility. As the E field increases, the energy of the electron increases and the electron can be scattered into the upper valley, where the density of state's effective mass is 0.55 m0. The larger effective mass in the upper valley yields a smaller mobility. This inter-valley transfer mechanism results in a decreasing average drift velocity of electrons with electric field, or the negative differential mobility characteristic. Figure 5.8 energy band structure for gallium arsenide showing the upper valley and lower valley in the conduction band. Carrier diffusion. There is a second mechanism, in addition to drift, that can induce a current in a semiconductor. We may consider a classic physics example in which a container, as shown in figure 5.9, is divided into two parts by a membrane. The left side contains gas molecules at a particular temperature and the right side is initially empty. The gas molecules are in continual random thermal motion so that, when the membrane is broken, the gas molecules flow into the right side of the container. Diffusion is the process whereby particles flow from a region of high concentration toward a region of low concentration. If the gas molecules were electrically charged, the net flow of charge would result in a diffusion current. Diffusion current density. To begin to understand the diffusion process in a semiconductor, we will consider a simplified analysis. Assume that an electron concentration varies in one dimension as shown in figure 5.10. The temperature is assumed to be uniform so that the average thermal velocity of electrons is independent of x. To calculate the current, we will determine the net flow of electrons per unit time per unit area crossing the plane at x0. If the distance L shown in figure 5.10 is less than the mean free path of an electron, that is, the average distance an electron travels between collisions, LVTHCN, then on the average, electrons moving to the right at XL and electrons moving to the left at XL will cross the X0 plane. Figure 5.10 Electron concentration versus distance. 1/2 of the electrons at XL will be traveling to the right at any instant of time and 1/2 of the electrons at XL will be traveling to the left at any given time. The net rate of electron flow, Fn, in the x direction at x0 is given by. If we expand the electron concentration in a Taylor series about x0 keeping only the first two terms, then we can write equation 5.29 as, which becomes, each electron has a charge, E, so the current is. The current described by equation 5.32 is the electron diffusion current and is proportional to the spatial derivative, or density gradient, of the electron concentration. The diffusion of electrons from a region of high concentration to a region of low concentration produces a flux of electrons flowing in the negative x direction for this example. Since electrons have a negative charge, the conventional current direction is in the positive x direction. Figure 5.11a shows these one-dimensional flux and current directions. Figure 5.11, a. Diffusion of electrons due to a density gradient. b. Diffusion of holes due to a density gradient. We may write the electron diffusion current density for this one-dimensional case, in the form where dN is called the electron diffusion coefficient, has units of cm²/s, and is a positive quantity. If the electron density gradient becomes negative, the electron diffusion current density will be in the negative x direction. Figure 5.11b shows an example of a hole concentration as a function of distance in a semiconductor. The diffusion of holes, from a region of high concentration to a region of low concentration, produces a flux of holes in the negative x direction. Since holes are positively charged particles, the conventional diffusion current density is also in the negative x direction. The hole diffusion current density is proportional to the hole density gradient and to the electronic charge, so we may write for the one-dimensional case. The parameter dP is called the hole diffusion coefficient, has units of cm²/s, and is a positive quantity. If the hole density gradient becomes negative, the hole diffusion current density will be in the positive x direction. Objective: calculate the diffusion current density given a density gradient. Assume that, in an N-type gallium arsenide semiconductor at temperature equals 300 kelvins, the electron concentration varies linearly from 10^18 to 7 times 10^17 per cubic centimeter over a distance of 0.10 centimeter. Calculate the diffusion current density if the electron diffusion coefficient is 225 square centimeters per second. Solution: the diffusion current density is given by. Comment: a significant diffusion current density can be generated in a semiconductor material with only a modest density gradient. Total current density. We now have 4 possible independent current mechanisms in a semiconductor. These components are electron drift and diffusion currents and hole drift and diffusion currents. The total current density is the sum of these 4 components, or, for the one-dimensional case. This equation may be generalized to 3 dimensions as: the electron mobility gives an indication of how well an electron moves in a semiconductor as a result of the force of an electric field. The electron diffusion coefficient gives an indication of how well an electron moves in a semiconductor as a result of a density gradient. The electron mobility and diffusion coefficient are not independent parameters. Similarly, the hole mobility and diffusion coefficient are not independent parameters. The relationship between mobility and the diffusion coefficient is developed in the next section. The expression for the total current in a semiconductor contains 4 terms. Fortunately, in most situations, we will only need to consider one term at any one time at a particular point in a semiconductor. Graded impurity distribution. In most cases so far, we have assumed that the semiconductor is uniformly doped. In many semiconductor devices, however, there may be regions that are non-uniformly doped. We will investigate how a non-uniformly doped semiconductor reaches thermal equilibrium and, from this analysis, we will derive the Einstein relation, which relates mobility and the diffusion coefficient. Induced electric field. Consider a semiconductor that is non-uniformly doped with donor impurity atoms. If the semiconductor is in thermal equilibrium, the Fermi energy level is constant through the crystal, so the energy band diagram may qualitatively look like that shown in figure 5.12. The doping concentration decreases as X increases in this case. There will be a diffusion of majority carrier electrons from the region of high concentration to the region of low concentration, which is in the X direction. The flow of negative electrons leaves behind positively charged donor ions. The separation of positive and negative charge induces an electric field that is in a direction to oppose the diffusion process. Figure 5.12 energy band diagram for a semiconductor in thermal equilibrium with a non-uniform donor impurity concentration. When equilibrium is reached, the mobile carrier concentration is not exactly equal to the fixed impurity concentration, and the induced electric field prevents any further separation of charge. In most cases of interest, the space charge induced by this diffusion process is a small fraction of the impurity concentration. Thus the mobile carrier concentration is not too different from the impurity dopant density. The electric potential is related to electron potential energy by the negative charge, so we can write. The electric field for the one-dimensional situation is defined as: if the intrinsic Fermi level changes as a function of distance through a semiconductor in thermal equilibrium, an electric field exists in the semiconductor. If we assume a quasi-neutrality condition in which the electron concentration is almost equal to the donor impurity concentration, then we can still write. Solving for F minus EFI, we obtain. The Fermi level is constant for thermal equilibrium, so when we take the derivative with respect to X we obtain. The electric field can then be written, combining equations 5.41 and 5.38, as: since we have an electric field, there will be a potential difference through the semiconductor due to the non-uniform doping. Objective: determine the induced electric field in a semiconductor in thermal equilibrium, given a linear variation in doping concentration. Assume that the donor concentration in an N-type semiconductor at temperature equals 300 kelvins is given by, where X is given in centimeter and ranges between 0 and 1 micrometer. Solution: taking the derivative of the donor concentration, we have the electric field is given by equation 5.42, so we have at X equals 0, for example, we find. Comment: we may recall from our previous discussion of drift current that fairly small electric fields can produce significant drift current densities, so that an induced electric field from non-uniform doping can significantly influence semiconductor device characteristics. The Einstein relation. If we consider the non-uniformly doped semiconductor represented by the energy band diagram shown in figure 5.12 and assume there are no electrical connections so that the semiconductor is in thermal equilibrium, then the individual electron and hole currents must be zero. We can write. If we assume quasi-neutrality so that N equals N donors, X, then we can rewrite equation 5.43 as: substituting the expression for the electric field from equation 5.42 into equation 5.44, we obtain. Equation 5.45 is valid for the condition. The hole current must also be zero in the semiconductor. From this condition, we can show that combining equations 546a and 546b gives the diffusion coefficient and mobility are not independent parameters. This relation between the mobility and diffusion coefficient, given by equation 5.47, is known as the Einstein relation. Objective: determine the diffusion coefficient given the carrier mobility. Assume that the mobility of a particular carrier is 1000 square centimeters per volt seconds at temperature equals 300 kelvins. Solution: using the Einstein relation, we have that. Comment: Although this example is fairly simple and straightforward, it is important to keep in mind the relative orders of magnitude of the mobility and diffusion coefficient. The diffusion coefficient is approximately 40 times smaller than the mobility at room temperature. Table 5.2 shows the diffusion coefficient values at temperature equals 300 kelvins corresponding to the mobilities listed in Table 5.1 for silicon, gallium arsenide, and germanium. The relation between the mobility and diffusion coefficient given by equation 5.47 contains temperature. It is important to keep in mind that the major temperature effects are a result of lattice scattering and ionized impurity scattering processes, as discussed in section 5.1.2. As the mobilities are strong functions of temperature because of the scattering processes, the diffusion coefficients are also strong functions of temperature. The specific temperature dependence given in equation 5.47 is a small fraction of the real temperature characteristic. Table 5.2 typical mobility and diffusion coefficient values at temperature equals 300 kelvins. Silicon electron mobility 1350 square centimeters per volt seconds. Silicon hole mobility 480 square centimeters per volt seconds. Silicon electron diffusion coefficient 35 square centimeters per second. Silicon hole diffusion coefficient 12.4 square centimeters per second. Gallium arsenide electron mobility 8500 square centimeters per volt seconds. Gallium arsenide hole mobility 400 square centimeters per volt seconds. Gallium arsenide electron diffusion coefficient 220 square centimeters per second. Gallium arsenide hole diffusion coefficient 10.4 square centimeters per second. Germanium electron mobility 3900 square centimeters per volt seconds. Germanium hole mobility 1900 square centimeters per volt seconds. Germanium electron diffusion coefficient 101 square centimeters per second. Germanium hole diffusion coefficient 49.2 square centimeters per second. The Hall effect. The Hall effect is a consequence of the forces that are exerted on moving charges by electric and magnetic fields. The Hall effect is used to distinguish whether a semiconductor is N-type or P-type 3 and to measure the majority carrier concentration and majority carrier mobility. The Hall effect device, as discussed in this section, is used to experimentally measure semiconductor parameters. However, it is also used extensively in engineering applications as a magnetic probe and in other circuit applications. The force on a particle having a charge q and moving in a magnetic field is given by where the cross product is taken between velocity and magnetic field so that the force vector is perpendicular to both the velocity and magnetic field. Figure 5.13 illustrates the Hall effect. A semiconductor with a current Ix is placed in a magnetic field perpendicular to the current. In this case, the magnetic field is in the z direction. Electrons and holes flowing in the semiconductor will experience a force as indicated in the figure. The force on both electrons and holes is in the y direction. In a p-type semiconductor P0 is greater than N0, there will be a buildup of positive charge on the y equals 0 surface of the semiconductor, and, in an N-type semiconductor N0 is greater than P0, there will be a buildup of negative charge on the y equals 0 surface. This net charge induces an electric field in the y direction as shown in the figure. In steady state, the magnetic field force will be exactly balanced by the induced electric field force. Figure 5.13 geometry for measuring the Hall effect. This balance may be written as which becomes the induced electric field in the y direction is called the Hall field. The Hall field produces a voltage across the semiconductor which is called the Hall voltage. We can write where E is assumed positive in the y direction and VH is positive with the polarity shown. In a p-type semiconductor, in which holes are the majority carrier, the Hall voltage will be positive as defined in figure 5.13. In an N-type semiconductor, in which electrons are the majority carrier, the Hall voltage will have the opposite polarity. The polarity of the Hall voltage is used to determine whether an extrinsic semiconductor is N-type or P-type. Substituting equation 5.50 into equation 5.49 gives. For a p-type semiconductor, the drift velocity of holes can be written as, where E is the magnitude of the electronic charge. Combining equations 5.52 and 5.50, we have, or, solving for the hole concentration, we obtain. The majority carrier hole concentration is determined from the current, magnetic field, and Hall voltage. For an n-type semiconductor, the Hall voltage is given by, so that the electron concentration is. Note that the Hall voltage is negative for the n-type semiconductor, therefore, the electron concentration determined from equation 5.56 is actually a positive quantity. Once the majority carrier concentration has been determined, we can calculate the low field majority carrier mobility. For a p-type semiconductor, we can write. The current density and electric field can be converted to current and voltage so that equation 5.57 becomes. The hole mobility is then given by. Similarly, for an n-type semiconductor, the low field electron mobility is determined from. Objective: determine the majority carrier concentration and mobility, given Hall effect parameters. Consider the geometry shown in figure 5.13. Let length equals 0.1 cm, width equals 0.02 cm, and depth equals 0.001 cm. Also assume that current X equals 1.0 mA, voltage X equals 12.5 volts, magnetic field strength Z equals 500 Gauss, which equals 0.05 Tesla, and VH equals 6.25 millivolts. Solution. A negative Hall voltage for this geometry implies that we have an n-type semiconductor. Using equation 5.56, we can calculate the electron concentration as. The electron mobility is then determined from equation 5.60 as. Or. Comment. It is important to note that the MKS units must be used consistently in the Hall effect equations to yield correct results. Summary. The two basic transport mechanisms are drift, due to an applied electric field, and diffusion, due to a density gradient. Carriers reach an average drift velocity in the presence of an applied electric field, due to scattering events. Two scattering processes within a semiconductor are lattice scattering and impurity scattering. The average drift velocity is a linear function of the applied electric field for small values of electric field, but the drift velocity reaches a saturation limit that is on the order of 10 million centimeters per second at high electric fields. Carrier mobility is the ratio of the average drift velocity and applied electric field. The electron and hole mobilities are functions of temperature and of the ionized impurity concentration. The drift current density is the product of conductivity and electric field, a form of Ohm's law. Conductivity is a function of the carrier concentrations and mobilities. Resistivity is the inverse of conductivity. The diffusion current density is proportional to the carrier diffusion coefficient and the carrier density gradient. The diffusion coefficient and mobility are related through the Einstein relation. The Hall effect is a consequence of a charged carrier moving in the presence of perpendicular electric and magnetic fields. The charged carrier is deflected, inducing a Hall voltage. The polarity of the Hall voltage is a function of the semiconductor conductivity type. The majority carrier concentration and mobility can be determined from the Hall voltage. Glossary of important terms. Conductivity, a material parameter related to carrier drift, quantitatively, the ratio of drift current density to electric field. Diffusion, the process whereby particles flow from a region of high concentration to a region of low concentration. Diffusion coefficient, the parameter relating particle flux to the particle density gradient. Diffusion current, the current that results from the diffusion of charged particles. Drift, the process whereby charged particles move while under the influence of an electric field. Drift current, the current that results from the drift of charged particles. Drift velocity, the average velocity of charged particles in the presence of an electric field. Einstein relation, the relation between the mobility and the diffusion coefficient. Hall voltage, the voltage induced across a semiconductor in a Hall effect measurement. Ionized impurity scattering, the interaction between a charged carrier and an ionized impurity center. Lattice scattering, the interaction between a charged carrier and a thermally vibrating lattice atom. Mobility, the parameter relating carrier drift velocity and electric field. Resistivity, the reciprocal of conductivity, a material parameter that is a measure of the resistance to current. Velocity saturation, the saturation of carrier drift velocity with increasing electric field.